So till now we have gone through what is Euler Totient function and all the three properties with their proofs, right? Now we arrive at the main event of this entire video, that is the formula of phi of n. It is n into 1 minus 1 by p1, where p1 is a prime number and it divides n. Similarly, p2 is a prime number that divides n. pk is also prime number that divides n. So this is the formula for phi of n. But how? Well, it's very simple. Let's go back to the example where n is 6. So let's compute the prime factors of 6, which are 2 and 3. Well, you have 6 numbers now. 1, 2, 3, 4, 5 and 6. See, these two numbers 3 and 6 are divided by 3, and these three numbers 2, 4 and again 6 are divided by 2. So what we can do, we know for sure that all these four numbers 2, 3, 4 and 6 cannot be co-prime with our given value, that is 6. We know that. So let's remove those. We have total number as 6. First we will remove all the numbers that can divide our p1. Here p1 is 2. So 6 by 2. Then we will remove all the numbers that are divided by p2. Here p2 is 3. So we remove all the numbers that are divided by p2. So that means we remove 2, 4 and 6. And we did this in this particular calculation. Then we remove 3 and 6 again in this particular calculation, right? So you are removing 6 twice. 2 times you have removed this. So you need to add it back, right? So you do 6 divided by 2 into 3. See, that's what we have done here. And if you take 6 common, you get this particular formula which exactly matches with the formula that is given to us. I hope this is clear. So by extending the observation that we have here, we can prove the formula by using inclusion exclusion. So you have n, you remove all the numbers that are divided by the prime factors of n. Then you need to add back all the numbers who got removed twice. Likewise, you take n common from this, and the remaining thing is something like 1 minus 1 by pi plus 1 by pi into pj, summation everywhere. Then you have 1 divided by pi, pj, pk, again here summation, something like this, n into, right? You can write this step in this form. This is directly from basics of algebra. So ultimately you have phi of n as n into 1 minus 1 by p1, where p1 is a prime factor of n. Similarly p2 is prime factor of p2 till pk, where pk is also prime factor of n. So by inclusion exclusion we can prove this particular formula. Now by using properties as well, the three properties that we discuss, you can prove the formula for n. See, let's say n can be represented like this: p1 to the power a1, p to the power a2, p3 to the power a3, like something like that. So by using the third property, let me write here, by using third property p3, what we can do, we can say phi of n is equal to phi of p1 to the power a1, p to the power a2, like p to the power pk to the power ak. After that, you can see we can write this pk to the power a power k as pk to the power a power k minus pk to the power ak minus 1, and this comes from property 2. You take this p1 common from here, p2 common from here, pk common from here, you will get something like this. Now you take this p1 to the power a1, p to the power a2, pk to the power ak together, and that value is n. So I have written n here, and what is remaining with you? This value, 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. So by using properties, this proof is very simple. So this is our main formula for computing Euler's Totient function, and we have managed to prove this particular formula with two different ways. One is inclusion exclusion, other is using properties. Proof by property is very simple. Inclusion exclusion, you need to have some basic understanding of algebra. So let's deep dive into the code. Remember, the formula is n into 1 minus 1 by p1 and 1 minus 1 by p2, something like that, right? So you need to compute the prime factors. That's the requirement. Let's say result is n initially, and then what we will do, once we found any prime factor of n, let's say I is a prime factor of n, then we are going to update the value of result. How we will update that? Remember, answer is n into 1 minus 1 by p. Here I is a prime factor. So result will be updated as result minus result by I. Right? And this is how result will be updated. That's what we have written here. So we are iterating from I is equal to 2 till I into I less than or equal to n. See, this is from basic algebra. Let's say you have a into b, which is equal to n. Then we can directly say either a is going to be less than n or b is going to be less than root n. How? Imagine both of them are greater than root n. Imagine that. Then what will happen? A into b. You can definitely say it is greater than root n into root n. Then you can say a into b is greater than n. But a into b is n. So you can never have both a and b being greater than root n. So you can have at most one number or one prime factor of n that is greater than root n. And that one prime factor is handled here. Remaining all prime factors we will handle in the loop. So if you observe carefully, the time complexity of this particular algorithm is just root n. Why? Because this for loop goes till root n. Even though this can go up to log of n, imagine I is 2, which is the smallest, and n being 10 to the power 18. Still, we are removing 2 every single time. That means this can go up to 60 only 60 iterations. Then that n will be reduced to 1 and this condition will break. So this will be run very small number of time. So ultimately time complexity is just root n for this entire algorithm. I hope this makes sense. So now we have the final code. This function will give you the direct answer for phi of n. But sometimes we don't just need phi of n, rather we need phi of every single value from 1 to n. So we need phi of 1, we need phi of 2, like that we need phi of n. We need to compute for every single number. So what will happen? It will be like root 1 plus root 2. In terms of time complexity, I am talking about root 3, something like that. But there is a better approach. If you observe carefully, if you look at this particular formula carefully, what we are doing, once we know that p1 is a prime factor of n, we are actually doing a simple multiplication here. And we do know how to compute prime factors, right? If you have any doubt in how to compute prime factors, please watch my sieve of Eratosthenes algorithm video. I will put that into the card. That is very simple. So first we initialize every single phi equal to that particular value itself. So how it will look like? Phi of 6 will be 6 initially. Phi of 6 should have been 6 into 1 minus 1 by 2. 2 is a prime factor of 6. And 1 minus 1 by 3, right? Initially, phi of 6 is just 6. Once we start this particular loop, look at this particular if condition. We are checking phi of I is equal to I or not. If phi of I is equal to I, then none of the previous number have divided it. Because if it would have been divided by any previous number, then it would have gotten updated. But none of the previous numbers have divided it. That means this particular I is a prime number. So we are going to take that number and update the value for all its multiple. That's what we are doing here, right? 2 is a prime number. So it will affect the value of 6, phi of 6. So if I is a prime number, then for every single j that is a multiple of I, we will update the value of phi of j, right? So if you look carefully, phi of 6 will be updated by 2 like this. Then I will become 3. Again, phi of I is still I. then we'll update the phi of j value as well. For 6, it will be updated again. Earlier it was 6 into 1 minus 1 by 2. Till here it got updated when we were processing 2, when I was 2. Now I is 3, so we are going to multiply it by 1 minus 1 by 3. And this is what our formula tells us, right? If you look at these two codes, see here what we are doing, we are computing for a single phi of n. So we are computing all of its prime factors and then we are updating the value of result. But in second case, we are not directly computing all of the prime factors. Rather, what we are doing, once we know that I is a prime number, then we are going to all its multiple and updating that phi value based on this I, right? For I is equal to 2, it will be 1 minus 1 by 2. And this value will get multiplied to every single j, that is a multiple of 2. For 3, it will be 1 minus 1 by 3. And this particular value will get updated for every single j, that is multiple of 3. I hope this makes sense. You can dry run this code. See, understanding Euler's Totient function is very important because it is used in modular arithmetic and lot of DSA problems and competitive programming problems. There are two different techniques that we learn here. First one was counting, which we used for proving phi of A into B is phi of A into phi of B. Right? We used here that counting technique. Also the second technique that we learned is inclusion exclusion. We learned 3 different properties and we went through the proof of all the 3. This video is very important. If you don't understand anything, please do comment. I will make another video by taking an actual problem. Watch this video twice or thrice for the better understanding.